Welcome to lecture 2 of our module on differentiation, numerical differentiation and integration. In the previous module what we did was several numerical differentiation methods to compute f dash and f double dash of xi were introduced. We looked at a method called method of undetermined coefficients in order to find out how to obtain these numerical derivatives and how to obtain the error function for those numerical derivatives. What we will do now and what we will start off with is we will start off with Microsoft Excel, so that we can show numerically that some of the concepts that we have learned in the previous lecture, how the error decreases when we change our delta x. One, the second part we will show is how the three different methods the error changes as delta x or delta x squared. That is what we will do next, and then we will see something interesting, that it is not always that as delta x is reduced we will get the error to reduce monotonically. We will see that at some point when delta x is reduced beyond a certain value, the error does not really reduce but it actually increases, and why that happens we will see that also in today's lecture. So that is the overall plan for today's lecture. We will now go to Microsoft Excel. What I have shown over here, we will take this particular f of x 2 minus x plus ln x and try to numerically derive f dash of x for this particular function 2 minus x plus ln of x. The analytical solution for f dash of x is minus 1 plus 1 divided by x. That is what we are going to get if we substitute any value of xi in this particular this particular equation. Okay. So what we will do is we will choose our xi, we will choose that equal to 1. So I will just increase the font size over here. So yes, so xi is chosen to be equal to 1. Okay, we will just format it so that looks better. Okay, so when xi is equal to 1, when we substitute x equal to xi in this particular equation, we get minus 1 plus 1 divided by x, which is equal to 1. So minus 1 plus 1, which is 0. So f dash at x equal to 1 is 0 for this particular equation. So any deviation from 0, we know that we do not have the correct the exact value. So what we will do is we will try to solve this particular problem for various values of delta x. We will take delta x equal to 1, 0 0.1, 0 0.01, so on and so forth. Okay, so I will just drag it down. Okay, equal to this divided by 10. Okay, for various values of delta x we have this x of I plus 1 is going to be, so we will have x of I plus 1 and x of I minus 1 as well. So x of I minus 1, and I will take this and increase the font size to 18 for all of these. Okay, so x of I minus 1 is going to be equal to x of I, and I will put dollar signs over there because x of I is not going to change, minus delta x. Okay, so this is what we will get. Actually I will not use delta x equal to 1 because log of x is going to be equal to log of x. We will not get anything if we are going to use that equal to x equal to 0. So that is why I will just eliminate that particular value. So this is going to be equal to x plus delta x, and as before we will put the dollars over here, and this is going to be this guy xi plus 2 is going to be xi plus 1 plus delta x. Okay, take this and drag it below. problem over here. I will just unmerge the cells, okay, and I think this should be fine now when we drag these cells over here. Okay, so these are the values of xi minus 1, xi plus 1 and xi plus 2. Although these values look 1 1 1 over here, it's only because we haven't given enough size for those cells. If we increase the size of the cells, let us say to this size, we will see that we actually get those values equal to something other than 1. Okay. So now we will have f of I minus 1, f of I minus 2, sorry, f of I plus 1 and f of I plus 2. Those are also some things that we will calculate. So that is equal to 2 minus x plus ln of x. So fi is fi minus 1 is going to be 2 minus this guy plus ln of again this guy, okay. So that is going to be our fi minus 1, okay, and we will just drag it. So we will get fi plus 1 and fi plus 2, okay, and then we will just drag and drop it over here, okay. So these are the values of fi minus 1, fi plus 1 and fi plus 2, okay. So now our f dash by central, and then we will calculate f dash by forward, and we will also calculate our f dash by 3-point difference formula. Okay, and I will just resize some of these so that we can view all the results simultaneously. Okay, so central CNTR. Okay, so f dash of central is going to be equal to f of xi minus f of xi minus 1. So fi plus 1 minus fi minus 1 divided by 2 times delta x, okay. So we have fi plus 1 minus fi minus 1 divided by twice delta x, and this is going to be our f dash of central difference formula. Keep in mind that our true f dash is equal to 0. So whatever f dash we get from the numerical value is the actual error also, because anything minus 0 is going to be equal to that particular value itself. I will just drag and drop it below. So we have the f dash using central difference formula is 3e minus 3, 3e minus 5, 3e minus 7, 3e minus 9, again 3e minus 11, so on and so forth. So what we see initially is that decreasing the delta x by a factor of 10, we are improving f dash by a factor of 100. So when delta x divided by 10 we choose, we will get our f dash x divided by 100. That is because, as we had seen, as we had derived earlier, the central difference formula is accurate to delta x squared. Let us see what happens with forward difference formula. For forward difference formula I will need f of xi. So f of I is going to be equal to, we will calculate that. So that value is equal to 2 minus xi plus ln of xi, okay. So f of I is going to be equal to 1 as well. Okay, I will just move this a little bit down so that we are clear of what we had upwards. Okay, so this is our xi, this is our f of xi. Again beautify it a little bit so that it is easier to see. Okay, so now our f dash using the forward difference method is going to be equal to f of I plus 1 minus f of I divided by delta x. Okay, and because f of I is not going to change, the cell, this green color cell has to remain the same when we drag and drag this contents of this cell. I will put the dollar signs over there and I will just pull this downwards, and this is what we are going to get. Okay, so what we get is f dash is the error for f dash using the forward difference method is starts off as a fairly high value over here. Okay, the error is fairly high, and as we decrease the overall delta x, the error keeps decreasing, and as we change the delta x, the error decreases more or less linearly. What that means is I decrease the delta x by a factor of 10 and the error decreases by a factor of 10, I decrease it by another factor of 10, error decreases by another factor of 10, so on and so forth. So what we see is we see a linear decrease in the overall error, that is what we observe in this particular case. And the 3-point forward difference formula that we are going to use is equal to minus 3 multiplied by our f of xi, and I will put dollar signs over there, plus 4 multiplied by f of xi plus 1 minus f of xi plus 2, the whole thing divided by twice delta x. Okay, so that is my equation over there, and then I just drag it, and again what I see is the error initially is 5 into 10 to the power minus 3, then it becomes 7e minus 3, 7e minus 7, 7e minus 9, 7e minus 11, and then the error again increases. Okay, let us try to do this for another value of xi, let us say xi equal to 2. Okay, and for xi equal to 2, this is going to be our f of xi, and our true value of f dash is minus 1 plus 0.5, so that true value is minus 0.5. So let us now look at the errors in these values. So the next 3 cases are going to be errors in the values. So I will just format this. Okay. Size it. Okay. So our true value that we know is minus 0.05. So absolute of minus 0.5 minus of the value that we obtain over there. Okay. So that is going to be our error, and then we will just drag it over here. Okay, and likewise we will just drag it in this direction. Okay, so what we see over here is for the central difference formula, the error starts at 4e minus 4, 4e minus 6, 4e minus 8, 4e minus 10, 4e minus 12, and then it starts increasing, the error starts increasing. Okay, for the forward difference formula, the error is 1e minus 2, 1e minus 3, 1e minus 4, 1e minus 5, and so on, and then after a certain point it increases, and same thing that we see for the 3-point forward difference formula also. So what we will now do is we will plot our errors against delta x. So I will just go out of the full screen mode, so that I can include the plots. So what I will do is I will select this delta x and I will select this error, and then I will go on to insert, and I will insert a scatter plot. Okay, so this is the plot that I have inserted over here. I will delete the legend, and what we want to do is plot it on the logarithmic scale, both for the x axis as well as for the y axis. Format axis, select the logarithmic scale. Okay. So, this is the overall plot that we get for the central difference formula. Okay. Likewise, now we will do the plot for the forward difference formula, and we will add another series. The x values remain the same, and the y values we will choose them over here. Okay. And we will add the errors for the third guy as well, and the x values again remain the same, and the y values that we are going to choose are the errors in the 3-point formula. Okay. Okay. So, the blue line over here corresponds to the, so on y axis we have the errors, and in the x axis we have the delta x's. 14, I will just again go ahead and format the number, I will use that as a scientific notation. Okay. And likewise, I will change this also to the scientific notation. Okay. So, this is the overall errors that we get, the red line indicating the errors for the forward difference formula, the blue line indicating the error for the central difference formula, and the green line indicating the errors for the 3-point forward difference formula. As we see is that the errors in the central difference formula are lower than the errors in the forward difference formula. However, in both the cases, in the forward as well as the central difference formula, as we decrease the value of our delta x, so there is an increase in the errors that we see after a particular point of time, and this is because of the truncation and round off errors. What happens initially is that the truncation errors keep decreasing and the round off errors are low enough. After a certain point, the round off errors start getting larger than the truncation errors. Okay. Keep in mind what is happening over here, what we observe over here is that for the central difference formula, the optimum value of delta x that we get is approximately 10 to the power minus 5 or 10 to the power minus 6, something in that ballpark range, whereas for the forward difference formula, the value for best delta x happens to be over here, which is approximately 10 to the power minus 8. So, the overall take home message was 1, the errors So, the overall take home message that we get from what the Excel results is that number 1 is that the errors in the central difference formula are typically tend to be lower than the errors in the forward difference formula. The second observation that we made is that the central difference formula, the value of delta x that gives the best value for the errors turns out to be approximately of 10 to the power minus 5 or maybe 10 to the power minus 6, whereas in case of the forward difference formula the best delta x occurs at around 10 to the power minus 8. We will see why that is in a short while from now. And the final thing that we observed is for pretty much the entire range of conditions, the central difference formula tended to be more accurate than the forward difference formula. Okay. So now I will go on to the board and try to explain why we get some of the observations. So let us now use the board in order to derive some error analysis results for numerical differentiation. So for forward difference, f dash of xi was equal to f of xi plus 1 minus f of xi divided by delta x, and the truncation error was of the order of delta x. So it was proportional to delta x. So I will use some kind of a constant multiplied by delta x. That particular constant was f double dash of zeta divided by 6 multiplied by delta x. Okay, and we do not worry whether the error is positive or negative. So we are going to put absolute values of this. Okay. So in addition to truncation error, there is also the round off error associated with the overall problem, but the actual round off error is going to be determined by the absolute value of f multiplied by the epsilon tolerance. As a result of this, we will get round off errors is going to be proportional to f of xi divided by delta x multiplied by epsilon machine precision. Okay. So that is going to be our truncation error. This fellow is going to be our round off error. So our total error E total is going to be just E truncation plus E round off okay, which we are going to write, let us call this f double dash zeta divided by 6 absolute value of that as alpha. So that we will write that as alpha multiplied by delta x, and let f of xi, let us call that equal to beta, the absolute value of f of xi we will call that as beta. So we will have beta epsilon precision divided by delta x. Okay. So that is our total error. Now we want to find out the value of delta x at which the total error becomes minimum. Okay. So if we were going to plot the truncation and the round of errors, okay. So we will start with a large enough value of delta x and we will start reducing the value of delta x. So the truncation error is proportional to delta x. So as delta x decreases, the truncation error will keep decreasing. So, the truncation error will decrease something like this. Okay. The round of error on the other hand increases as the delta x decreases, or it decreases as delta x increases. So, for example, if we are going to start with a very low value of delta x, there will be a fairly large round of error in delta x, and as the delta x keeps increasing, the round of error is going to decrease simply because delta x is in the denominator. So, this is how perhaps the round of error is going to look like. Okay. So, if we sum these two guys up, the total error will look somewhat like this. Okay, with the minima happening at a particular value of delta x. We will call that as delta x minima, or delta x where there is the minimum total error in the numerical derivative. Okay. So, this is what we are going to get, and clearly the delta x that is going to minimize the total error is going to be given by d delta x of E total, which is going to be equal to d by d delta x of alpha delta x plus beta epsilon by delta x equal to 0, which is going to be equal to alpha minus beta epsilon by delta x squared equal to 0, or we will write alpha equal to beta epsilon by delta x squared, and which will yield us delta x that gives the minimum value of the error is going to be proportional to epsilon to the power half. Okay. Now, our machine precision for double precision machine, the machine precision, that's double precision is what Microsoft Excel uses, is of the order of 2 multiplied by 10 to the power minus 16. Okay. So, the best value of delta x for forward difference is 2 to the power 10 to the power minus 16 to the power half, and that is of the order of 10 to the power minus 8. Okay. And if you recall what we observed a few minutes earlier, we actually observed that the error when we started off with delta x equal to 0.1 and we started decreasing the delta x, we found that the error happened, the minimum error happened at around 10 to the power minus 8. Okay. So, this is what we observed with the forward difference formula when we solved it in Excel. Now, we will do this entire derivation again for the central difference formula. Let me remind you the result that we got from Excel using the central difference formula. The delta x minima for central difference formula if you remember was of the order of 10 to the power minus 5 to 10 to the power minus 6. Approximately in that range is what we had obtained in Microsoft Excel. Let us try to use the same idea in order to derive for the central difference formula. The central difference formula was f dash of xi equal to f of xi plus 1 minus f of xi minus 1 divided by 2 times delta x, which is equal to, or the truncation error, the round off error in this particular case is equal to some alpha multiplied by delta divided by delta x, where alpha in this particular case is going to be absolute value of f of x I plus 1 divided by 2. That is what the round of error is going to be proportional to. The truncation error if you recall the truncation error in the central difference formula, the central difference formula was the second order accurate in delta x. So, the truncation error we can say is beta delta x squared. This beta was minus 1 divided by 12 f 4 dash of zeta, okay. So, this beta was, or the absolute, we have to take the absolute value. So, it was 1 divided by 12 f 4 dash of zeta. That was what the value of beta we had obtained through the derivation. As a result, E total is going to be alpha by delta x plus beta delta x squared, okay. And to find out the value of delta x, for which we get the error to be minimum, what we are going to do is we are going to differentiate this particular guy d by d delta x and equate it to 0, okay. And the result is going to be fairly straightforward. We are going to get minus alpha by delta x squared plus 2 beta times delta x equal to 0, or we'll essentially get we take alpha delta x squared onto this side, we will have delta x cubed. Oh, I am sorry, what we should have over here is round of error is proportional to alpha epsilon precision by delta x. So, I missed that. Okay. So, what we will get here is alpha by 2 beta times epsilon precision, or our delta x is going to be proportional to epsilon precision to the power 1 by 3, okay. And epsilon precision, as we said, was 2 into 10 to the power minus 16 to the power 1 by 3 is approximately in the range of 10 to the power minus 5 to 10 to the power minus 6, okay. So, this is the result, this is the reason why we get the central difference formula, the delta x should be chosen to be cube root of the machine precision, okay. So, that is really what I wanted to cover for the error analysis. In the same manner, we can do error analysis for the central difference formula to get the second derivative. The second derivative is f double dash of xi equal to f of xi plus 1 minus 2 f of xi plus f of xi minus 1 divided by delta x squared. E round off is of the order of alpha epsilon divided by delta x squared, and E truncation is proportional to beta delta x squared, okay. The central difference formula for f double dash is second order accurate. So, d by d delta x of E total is going to be equal to minus alpha epsilon by minus 2 alpha epsilon by delta x cube plus 2 beta delta x equal to 0. So, we rearrange, we divide by beta over here, and so what we will get is delta x to the power 4 is going to be equal to alpha by beta epsilon precision, okay, or delta x minima is going to be proportional to epsilon precision to the power 1/4. Okay. So, this is what we will get with respect to the error analysis. So, let me now summarize what we did in error analysis, and let us then come up with what are really the ways to use numerical differentiation. Okay. So, as delta x decreases, truncation error decreases, and round off error increases. Okay. So, there exists delta x for which the total error is minimum. Okay. So, for forward difference, okay, for the forward difference formula, our delta x has to be proportional to epsilon to the power half. For f dash using central difference or f dash using 3-point forward difference, delta x is proportional to epsilon to the power 1/3, and to use f double dash using central difference formula, delta x is going to be proportional to epsilon to the power 1/4. Okay. I am just stopping over here mainly because f dash using forward difference, f dash using central or 3-point difference, and f double dash using the central difference formula are likely the most common numerical differentiations that a typical chemical engineer encounters. So, I will not go into anything beyond that. Now, question is, how do we choose the actual delta x when we are going to implement, okay, and the way we choose the actual delta x is, let us say we want to find out f dash of xi. Keep in mind all these are in relative terms, they are relative with respect to the absolute values of the current system that we are looking at. So, if we want to find the numerical derivative of f dash, okay, if we select, let us say we have selected the forward difference scheme, then our delta x is going to be equal to the absolute value of xi multiplied by epsilon to the power half. Okay. Do not just use epsilon to the power half, it is the absolute value of xi multiplied by epsilon to the power half. So, xi is going to be equal to xi plus this guy for xi plus 1. So, xi plus 1 is going to be equal to xi plus xi epsilon to the power half. Okay. So, if xi is positive, then xi plus 1 is going to be equal to 1 xi multiplied by 1 plus epsilon to the power half. Okay. So, that is the choice that you need to take with respect to what delta x you will choose for getting the numerical derivative. Now, if you want to get the numerical derivative f dash using central difference formula, it is going to be absolute value of xi multiplied by epsilon to the power 1/3. because this is what we get over here. Okay. So this is how we are going to practically implement the overall use of numerical differentiation. Okay. So to summarize what we have done in numerical differentiation, what we started off with was we just said that geometrically numerical differentiation means finding the slope of a particular curve, and then we saw the forward, central and backward difference methods and the geometric interpretation of using them. Next we used the Taylor series expansion in order to derive the forward and central difference formula for f dash x and the central difference formula for f double dash x. Then we went on to a method called the method of undetermined coefficients in order to get the derivation for fx and f dash x. So that is what we covered with respect to deriving this overall formulae. After that we covered the error analysis, the truncation error. We saw that the error in f dash x was proportional to delta x for the forward difference formula, what was proportional to delta x squared in the central difference formula, proportional to delta x squared in a 3-point forward difference formula. Then we saw that as delta x is changed, round of error increases as delta x decreases, the truncation error decreases as delta x decreases, and there is a particular value of delta x at which the error is minimum. And then we finally derived the condition for which delta x is minimum, and we finished off by giving practical hints as to what delta x that we need to choose such that this particular error in finding out the numerical derivative is minimized. Okay. So that is essentially what I intended to cover in numerical differentiation. Now we will go to the second part of this particular module, and that is numerical integration. So now we go on to numerical integration. As we had said earlier, numerical integration is nothing but finding the area under a curve. So in fact not just numerical integration, integration in general is finding the area under a curve. Okay. So let us say we have some curve f of x, okay, and we want to find the integral of f of x dx. Okay. So this integral of f of x dx is nothing but this particular area under the curve. Okay. So geometrically what are the various ways to approximate that area? Okay. So geometrically the various ways to approximate the area under the curve is basically this particular interval we can split into many intervals, since the splitting up could usually is going to be our choice. We will split up into various equally spaced intervals and then find the area under the small part of the curve for each of these intervals. Okay. So let us say that the entire region I have split into various intervals, and the smallest interval is now represented as this particular curve. Okay. So what I have done is, for this curve I have looked at the smallest interval and then I have zoomed in that particular smallest interval, and let me call this the smallest interval rather than going from A to B. Let me call this going from say x1 to x2. Okay. And now I want to find out the integral going from x1 to x2 of f of x dx. Okay. So what I will do is I will find out integral from x1 to x2 f of x dx, x2 to x3, x3 to x4 and so on, starting with x1 equal to a and ending at xn equal to b. So that is the strategy that I will do. Okay, so now we zoom in into one particular interval and try to see what are the different ways. Okay, and the different areas that one can possibly think of is, you connect this particular horizontal line and the area under this yellow line is going to be one possible way of approximating that area under the curve. The other possible way of approximating the area under the curve is take this particular line and complete the rectangle over here. So that is the purple area. Okay, so the first area is the yellow rectangle, the second area is the purple rectangle, okay, and the third area is you connect this point with a straight line, and the third is the area under the trapezoid. Okay, so based on this we have three different numerical approximation. The yellow numerical approximation is going to be Euler's backward method, okay, in which the integral I, we will write that equal to f of x1 multiplied by x2 minus x1. Okay, the length of this segment is x2 minus x1, the length of this segment is f of x1. So the integral I is going to be nothing but f of x1 multiplied by x2 minus x1. The Euler's forward method is going to be I equal to f of x2 multiplied by x2 minus x1. Okay, so this is f of x2 and this particular area for this rectangle is f of x2 multiplied by x2 minus x1. Okay, that is the Euler's forward method. And the third method that we talked about is called the trapezoidal rule. Okay, and in trapezoidal rule I is going to be equal to the area under the trapezoid. The area under the trapezoid is, if we remember from our basic geometry, is nothing but this length multiplied by this length plus this length divided by 2. Okay, so the trapezoidal way is going to be b, that is the breadth, multiplied by L1 plus L2 divided by 2. That is the area under a trapezoid. We will substitute those values over here. Breadth is nothing but x2 minus x1, okay, and we have this term half multiplied by f of x1 plus f of x2, right. It is half multiplied by breadth multiplied by first length plus the second length, okay, and that is going to be the trapezoidal rule. Okay, so based on the geometric interpretation we have the Euler's backward method, Euler's forward method and the trapezoidal rules. These are the three different ways. These two methods are first order accurate in delta x. If we call this difference as delta x, or let us call this as using a simpler notation h, if we call this particular difference as h, the Euler's backward difference method is order h accurate, the forward difference method is also order h accurate, the trapezoidal rule is order of h squared accurate. Okay, so what we are actually going to do in the next lecture onwards is going to derive this trapezoidal rule. We will actually derive, so this is using the geometric method that we have derived trapezoidal rule. We will derive the trapezoidal rule once again using three different methods in the next lecture, and then we will go on to higher order formulae. These particular formulae are clubbed under the name Newton-Cotes integration formulae. Okay. In the forward and backward Euler's method, we use the function value only at one point and create a rectangle. In case of trapezoidal rule, we use the function value at 2 points and create a rectangle. We have higher order Newton Cotes formulae where we will use 3 points, 4 points and so on and so forth in order to create a more accurate method. Okay, and so essentially what we are going to see in the next lecture is this, is let us say we have an arbitrary curve of this sort, okay, and we want to find an integral between a to b. Okay, one possible thing is to take this particular midpoint which is a plus b by 2, okay, and of course one thing we can do is we can construct a trapezoid between the first 2 points and another trapezoid between the next 2 points and get the area under the curve. Other alternative is to connect these 3 points with a second order polynomial curve, and that second order polynomial curve is probably going to look like this, and so the area under the red curve can be obtained as a better approximation of the true area, and this particular red curve will be known as Simpson's 1/3 rule. Okay, if instead of 3 points we are going to join a third order curve to the 4 data points, we will get Simpson's 3/8 rule and so on and so forth. We can go to higher order rules as well. Usually we do not go beyond the Simpson's 3/8 rule, and we will see why that particular thing happens, or that particular thing is what we do in the next lecture. Okay, and after that we are going to cover the overall derivations and the error analysis of all these methods. So that is going to be our strategy for the next lecture while covering the numerical integration formulae. Okay, thank you, and I will see you in the lecture 3.